Today we are discussing about the concept of bond energies, and when we refer to bond energies in particular, we are referring here to the covalent bond. Okay, how we express that energy of that covalent bond, how can we identify what bonds are stronger than others, and how that's related with the multiplicity of the bond. So keep in mind, again, this is about the covalent bond. The covalent bond has to do with a concept that we already know, and that is the atomic size, the atomic radii. Here, the bond length, pretty much on the line of the atomic radii. Here is the internuclear distance between the two atoms in the molecule, and by two atoms we are referring, yes, the distance between the nuclei. When we were discussing the atomic radii, we were assuming that the the two atoms were of the same element. When you're referring here to a bond, yeah, it's open to every element in the periodic table, any combination that you may have. You want to know what the distance between the two nuclei, whatever they are, is for the bond length. Now, here is the full distance. Remember that. For the atomic radii was half the distance between the nuclei. Here for the bond length is the full distance. Okay, you don't have to divide by 2, it's just the distance between those two nuclei. Here we have an example that I think we have seen this before: fluorine, chlorine, bromine, and iodine. Okay, the larger the atom, of course, the longer the distance between these two atoms. And remember, if you are trying to compare the distance between the atoms, basically what you are doing is, if you keep in mind how the atomic size changes, then you would know how the atomic bond between different elements will change according to the atomic size. However, if we keep in mind, here we are more interested in the multiplicity of the bond. So if you have that the bond multiplicity increases, like meaning you are going from single to double to triple, then the bond length decreases. And there are two different things here that we're going for. One is the distance between the bond length itself, and the other one is the strength of that bond, how it changes when you change the multiplicity. Here, let's keep the direction going from single to triple, meaning you are increasing the multiplicity of the bond in both cases. But if you go in that direction, if you go from single to triple, when it comes to bond length, then the bond gets shorter. But at the same time, as the bond gets shorter, then when you think in terms of the strength, if you go from single to triple, then the bond gets stronger. Okay, so two things to remember here in terms of trends. If the multiplicity increases, if you go from single to double to triple, the bond gets shorter, but the bond also gets stronger. So those are two things to remember. So we can also see this in terms of the quantitatively, meaning here we are comparing bond length again, and here we are having the single carbon-carbon, double carbon-carbon, and triple carbon-carbon. This is a distance, as this unit is angstroms, and the angstrom is equal to 10 to the minus 10 meters. So it's a little smaller than the nanometer, but this is how back in the day things in the atomic size were being measured. Now, it doesn't matter what type of bond you are looking at. If you increase the multiplicity, the bond will get shorter regardless of what you have there. So, but try to keep in mind that you are trying to compare same bonds, correct? So here is, I mean, not same bond, but the same atoms connected. So here you are exploring the multiplicity of the carbon-nitrogen bond. If you go from single to double to triple, then those bonds will get shorter and shorter and shorter. Same thing if you have carbon and oxygen. Okay. One other thing that you can also explore here, probably not so clear between carbon and nitrogen and carbon oxygen, But remember, carbon is larger than nitrogen, and nitrogen is a little larger than oxygen. Or let's put it this way: they get smaller in that direction. So oxygen is the smallest of the three. So you may expect that the bond distance between a carbon-carbon would be longer than a distance between a carbon-nitrogen. Well, here is not such a good example to explore with nitrogen and oxygen, but you get the idea here, right? So when it comes to the energy of that bond, we can do exactly the same thing. So remember, in this direction gets shorter, in this direction gets stronger, and is looking at the energy of the bond itself. Okay, so the carbon-carbon single bond is this energy is how much energy you have to provide to break that bond. Okay, so you need to provide much more energy to break a triple bond than it is to break a double bond, and than it is to break a single bond. No matter what atoms you are exploring here in terms of connection, the trend is the same. The triple bond will always be stronger than the double bond, and the double bond stronger than the single bond, no matter what atoms you are connecting here. Okay, so this is the trend that you have to remember. What happens with the bond length, and with the bond energy as you increase the multiplicity, if you go from single to double to triple bond. Now we are talking about this energy, the strength of this covalent bond. So that bond energy is actually the bond dissociation energy. It's also an energy requirement, okay? It's a requirement. As such, is going to be always positive. So the bond energy will be always positive, and it's the energy that you need, that you require to break that particular bond. So the overall reaction is, if you have two atoms connected, well, whatever the bond is, if you separate those atoms, then that energy requirement is what you call the bond dissociation energy. So for example, hydrogen here, to break the hydrogen molecule into the two hydrogen atoms, then you require about 436 kilojoules, okay, according to that reaction. Now, if you look at this molecule, this is the methane molecule, and you're breaking the molecule into the carbon atom and the 4 hydrogen atoms. Here, the total energy that you need to break that is 1660 kilojoules. But the thing that you have to keep in mind here is that you are not breaking just one single bond here. Okay, you are breaking actually 1, 2, 3, and 4 carbon-hydrogen bonds. So if this is the total energy that you require to break that bond, then actually the bond dissociation energy for the carbon-hydrogen bond is going to be equal to 1660 kilojoules divided by 4, and that is about 415 kilojoules. So that's the energy that you require to break just one single bond. Okay, one single carbon-hydrogen bond. Here in the reaction above, you are breaking 4 carbon-hydrogen bonds. Okay, so how do we use this in a more practical way? Well, we can use this to do stuff that you have already done in the past. So how about calculating enthalpies of reaction for that matter? So here we have the reaction, the combustion of methane, and we want to know, based on bond energies, well, what is the enthalpy for this reaction. So the way we calculate this is that you have to focus on what bonds are being broken and what bonds are being formed. In this case, the bonds that you are breaking are the ones that are in the reactant side. The bonds that you are forming are the bonds that are in the product side. So here, pretty much what we are trying to say here is that is the sum of the energies, the bond energies of the reactants minus the bond energies of the products. And this is about the only time that you're gonna see that when you're calculating enthalpies, this is kind of the reverse. Whenever we are using functions of state, it's always the final state minus the initial state, except for this particular case. In this particular case, it's reactants minus products. So be careful with that. Now, in this case, it would be easier if we look at this reaction in the structural with the structural formulas, because then you can picture what the bonds are more easily. So in the case of methane, we have 4 carbon-hydrogen bonds. These are 2 molecules of oxygen, so it's plus 2, and the oxygen molecule is bonded by double bonds. And here you are obtaining 1 CO2 molecule, which has 2 double bonds, carbon-oxygen, and you are obtaining 2 molecules of water that are oxygen-hydrogen bonds. So, and structurally, this is what's happening. So what are the bonds that you have there? On the right, on the left, you have the bonds that are being broken, and on the right are the bonds that are being formed. So the way that I want you to approach this problem is you can use a table like this. Just at the beginning, try to do the table like this, and as you do exercise, it would be less and less necessary to do it, but this is still to make it a little more clear what's going on here. So we are taking a look at the reactants first, and in the reactant side you have 4 hydrogen carbon bonds. How many? You have 4, right? So here the total energy of those bonds that you're breaking are 1660. Correct? What else you have on the reactant side? You have 2 double oxygen-oxygen bonds, and breaking those 2 bonds require 996 kilojoules. Now, the reactant side, there is no carbon oxygen double bond, and there is no hydrogen oxygen bond, so there is nothing to add there. If you add those 2 things together, you obtain 2656. So that's the total energy that is required to break the bonds on the reactant side. Now when it comes to bonds formed, so you have in CO2 there are 2 carbon oxygen double bonds, and you have there are 2 water molecules. Each one has 2 oxygen hydrogen bonds, so you have a total of 4 here. Okay, there is no carbon hydrogen bonds, there is no oxygen double bond, so these we forget about those in the product side. Now here the total energy that it's associated with the CO2 is 2 times 6, 7, 41, so that's 1482, and for the oxygen hydrogen bonds is 1856. You add this together, then it is 3338 kilojoules. Now this is the energy associated with each side of the reaction. If you are going to calculate the enthalpy of reaction, then your enthalpy of reaction is going to be equal. Remember, this is the only case in which you have reactants minus products, so it is 2656 minus 3338, and that is going to be equal to minus 682 kilojoules per mole. Okay, so this is this example. Let's do another one. So in this case, again, you already have the structural formulas here. Remember, if you don't have the structural formulas like in this previous case, then you need to write it. So sometimes you might have to apply the Lewis structure rules and draw the molecule before you can actually start doing your calculations, because it matters. Remember, the bond energies differ according to double, triple, single bond. So you need to make sure you know what are the bonds that are being formed, what are the bonds that are being broken. So in this case, you have the structural formula, which makes things a little easier. So what we see here, and you know what, there is a 2, there should be a 2 there. okay, because there are a total of 4 bromines there. So what you see here, what you start with the reactant side. In the reactant side, what you have is 2 bromine bonds, okay, and then you also have 1 and 2 carbon hydrogen bonds, and last but not least you have a carbon triple bond. You are adding all that together, and now we are going to subtract everything that is on the product side. So what you have in the product side? In the product side, we are to add everything together, and then we subtract that from the reactants. Remember that. So what we have there? Well, we also have 2 carbon hydrogen bonds, 1 and 2. We don't have a carbon-carbon triple bond. We have a carbon-carbon single bond now. And last but not least, let's close this. We have 1, 2, 3, and 4 carbon-bromine bonds. So if we put this as an equation, then it is 2 times the bromine bond is 193, plus 2 times the carbon hydrogen bond is 414, plus the triple bond is 837, and we are to subtract everything else. Again, 2 times carbon hydrogen 414, plus the carbon single bond, which is 347, and 4 times the carbon bromine bond, which is 276. Okay, one thing to notice here, you have 2 carbon hydrogen bonds here. You also have 2 carbon hydrogen bonds there. And so you are adding here, you are subtracting there, so you can actually forget about those, because they are not, I mean, technically during the reaction you are not breaking the carbon hydrogen bond, so you can exclude those from the calculation. You have to be careful though. You have to do a good balance of what's being broken and what's being formed, just so you know. So in this case, then it's all reduced to 386 plus 837 minus 347 minus 1104, and that should be equal to, let me do this calculation quickly. Minus 228 kilojoules per mole. Okay. Now, one thing that I also want you to keep in mind, okay, this calculation here is the enthalpy of the reaction. It should be equal to everything that we have here. But thinking of this in terms of an equation, so the enthalpy of reaction is the sum of those bond energies. I mean, you adding, subtracting, and depending on the number of bonds that you're breaking and you are forming. But as an equation, think in terms that you can calculate anything out of that equation. For example, I can give you the enthalpy of the reaction, and then I would ask you to calculate the bond energy for a particular bond in that reaction. Could be on the reactant side, could be on the product side, but you can, I mean, once you set up your calculation in this way, you can calculate anything that you want. Okay, so that's it for now.